When we build massive, sweeping architectural spaces, like stadiums or ultra-tall high-rises, we are putting them directly in the crosshairs of extreme environmental threats. Freezing climates eat away at foundations, and earthquakes can force thousands of tons of steel and glass to sway violently. To survive these forces, relying on heavy, passive blocks of stone and steel is no longer a viable option. Modern structures have to function as highly engineered reactive systems that actively resist the environments trying to tear them down. Designing those survival systems is the focus of Yousef Bahrambeigi, an award-winning PhD researcher in civil and structural engineering. Bahrambeigi holds active memberships in the American Society of Civil Engineers, alongside the Iranian Societies of Structural Engineering, Concrete, and Space Structures, while simultaneously serving on the ground as a chief inspector. Through his extensive research, Bahrambeigi treats the modern building as an integrated organism, where the chemical composition of the material, the geometry of the frame, and the digital monitoring systems work as one synchronized unit. This integration begins with the concrete foundation. In harsh climates, the primary threat to that foundation is the freeze-thaw cycle. Water seeps into the concrete, freezes, expands, and systematically destroys the material from the inside out. Bahrambeigi's research identifies that macro-level structural failure starts at the nano-level. His work focused on creating high-performance concrete by blending in specific nano-additives, titanium dioxide and nano-calcium carbonate. This microscopic cross-section shows how those materials work. Instead of leaving open pores for water to infiltrate, the nano-additives bond with the concrete to form a dense, impenetrable network. When brutal freezing conditions hit, the moisture is physically blocked, preventing the microscopic cracking that leads to total failure. Securing the chemistry of the foundation at a microscopic level is a prerequisite. Without it, the massive macrostructural frameworks built on top of it cannot survive over time. Once the foundation is secure, the challenge moves to the geometry of the structure itself. To create massive, column-free architectural spaces, like arenas or exhibition halls, engineers rely on frameworks known as double-layer dome space structures. Looking at this 3D model, you can see how a double-layer dome distributes weight across a complex web of interconnected struts and nodes. It is incredibly efficient, but that immense geometric complexity makes it vulnerable. If the load-bearing math is off by a fraction at a single node, the entire web can buckle. To solve this, Bahrambeigi authored specialized research and a published book detailing how to use Ansys software to perform nonlinear analysis. As the dome is subjected to heavy loads, this analysis maps out exactly how the materials bend, yield, and distribute stress in real time, predicting failure points before they occur. As architectural shapes become increasingly unconventional, this kind of advanced computational mapping is a reliable way to predict load paths and prevent collapse. Supporting those complex roofs requires the steel framework. The engineering challenge here is maximizing structural strength while minimizing the sheer weight and cost of the steel. Bahrambeigi tackles this using advanced mathematical tools in MATLAB. By applying algorithms, specifically the sine-cosine algorithm and the Rosenberg algorithm, he calculates the exact geometric configurations that yield maximum material efficiency. But holding up static weight is only half the battle. The ultimate dynamic threat that tests this optimized framework is a catastrophic earthquake. To combat seismic threats, Bahrambeigi applies his research to practical scenarios, like designing a sophisticated base isolation system for a 10-story building, with each floor spanning 400 square meters. This diagram illustrates the mechanics of that seismic defense, building on his prior research with physical shake table testing. Instead of anchoring the building directly to the violently shaking earth, the foundation rests on specialized isolator pads. As the ground moves, the isolators compress and shift sideways, absorbing the kinetic energy and keeping the 10-story structure above nearly stationary. True structural optimization requires engineering that actively neutralizes unpredictable external kinetic forces. So, a building is constructed. It has chemically resilient concrete, a mathematically optimized steel framework, and base isolators for earthquakes. The ongoing challenge is ensuring that hidden structural health remains intact over a lifespan of 50 or 100 years. Bahrambeigui's most recent research addresses this by looking to the future of structural monitoring using artificial intelligence. This blueprint visualizes how AI integrates into physical infrastructure. By processing continuous data from sensors embedded within the walls, AI functions as a sensory network. It monitors the building for microscopic stress, material fatigue, or anomalies, identifying critical vulnerabilities long before they are visible to the naked eye. With AI integration, buildings transition from being static objects into reactive, self-diagnosing entities that can provide real-time data on their own maintenance needs. Bahrambeigui's career trajectory spans the development of these systems, starting with solving foundation issues through concrete chemistry in 2016 and moving to the use of AI to oversee those structures in 2024. His theoretical research is grounded by practical leadership. He has shared this knowledge as a university instructor and served on the Professional Ethics Committee for the West Azerbaijan Engineering Organization. His methodology tracks the entire life cycle of modern infrastructure, from the specific nanoparticles in the cement to the algorithms monitoring the roof. As the built environment faces more volatile conditions, civil engineering is shifting toward these intelligent, optimized systems, structures designed to withstand the unpredictable and protect the people inside them.